Hi, so I'm going to show you how to divide by 2. Well, it's not that simple. So the idea here is that we have a language L, and I'm going to define half of L to be all of the first halves of the strings in L. So more formally what that means is I'm going to take all the strings W, that's going to be the result set, and all the strings W such that there exists a Y. So the Y is the second half of the string, where putting them together is in L, and the two pieces are exactly the same length. So it really is the same length of the two halves here. So effectively, we're going to throw away any string from L that is of odd length, only keep ones of even length, and of the even length ones, we take away the first half of the string, the second half of the string, and we keep the first half of the string. That's what half of L is. So let's do an example. So let's let L just be a simple language. Let's let it be 0, 0, 1, 0, 0, 0, 0, 1, 1, just as an example. So then what is half of L then? Well, we're going to throw away any string of odd length, so the 0 is just going to be thrown away completely. And among the ones that are of even length, which are these 3, we're going to take the first half of that string. So the 0, 1 string, we're only going to take just a single 0. The 0, 0, we're going to only take the first half, which is just that 1, 0, which we've already taken already. And this string over here, we're going to take the first half of it, which is just these first two characters, and so we're going to have 0, 0 for that part. So half of L is just these two strings. Even though we had 4 strings before, we're going to have fewer than that number of strings in general. Okay, so what I want to prove here is that you can divide by 2 with regular languages. So we're going to show that if L is regular, then half of L is regular too. And this may seem a little interesting in the sense of not true, because if we think of, say, like a non-regular language, then taking the half of the language might be regular. So as an example, if we take 0 to the n, 1 to the n, where n is at least 0, that's not regular. So let's say that L is that. Well, then half of L is going to be just 0 star, because we just take the first half of the strings, and those are just the zeros at the beginning. And that is regular. So there's got to be something really interesting here, that it's not always the case that half of L is regular, but if the original language is regular, then half of L is regular. So the way that we're going to, of course, prove this is we're going to do it via deterministic finite automata, DFAs. So let's let D be a DFA for L. Okay, and we obviously don't know what this DFA may look like, and it may have any number of final states, transitions, we don't know. But let's try to visualize what happens. So let's let this thing be D right here. And we got some start states, some states in the middle potentially, and some final states potentially. Okay, well, let's say that we are looking at some string that is in this language, which means it does end up in a final state when ran through this DFA. And let's say that it's a somewhat long string. And let's assume that it's even length, because all the odd length strings are thrown away anyway. So let's say that we have something like this. So here, let's assume that this is the W part, which is the first half of the string, and here's the Y bit. And of course, let's assume, just for the sake of argument, that these are the same length. Okay. So this is saying that we're assuming that WY is accepted by this thing, because I drew it that way. And we're going to assume that they're the same length. Then, well, the thing is that we don't know the string in advance. We don't know where to start. We don't know where this middle point is necessarily. It could be any one of the states at all. And yeah, we don't know where the midpoint is because we can't jump ahead into the string, figure out where we'll end up, and then figure it out from there. That's just not possible. So what can we do instead? Well, what we can do is we don't know where this middle state is right here, so let's guess it. Let's use nondeterminism to guess what the middle state is. And then after that, figure out what to do. So let's try this idea. So this is not the DFA that we're going to build. This is the idea. So let's make a start state out here. And let's have an epsilon transition to every state in this entire thing. Okay, this might take a bit of work. But I'm going to have an epsilon transition to every single state in here because any state of this machine could technically be the middle state in the computation of this string that we're going to eventually read. We don't know what state it is. Let's just guess it. The problem is, well, this allows us to start anywhere, and what we need to interpret this as being as the state that we guess is to be the one in the middle. So that means that if we end up in, so let's think about it from the original machine's perspective. So let's say we guess this state right here. Then that's the middle state in the computation. Well, what we want to do is if we guess this thing, that we're going to read the string in somewhat of a different way. So we're going to somehow read it from the beginning here and the middle right here. And then let's see if we end up in the first half of the computation at the state we started at, and the second half in the second part of the string, which we don't care about because we don't care about the second half of the string for acceptance purposes, then we're going to hope that that ends up in a final state. So we need to keep track of what state we initially selected non-deterministically, as well as what is the first half of the computation doing, and also what is the second half of the computation doing. So let's try to make that a little bit more formal. So we're going to, let's let that machine D, I'm going to call its states Q, alphabet sigma, although that's not as important, delta, start state is Q0, and final state's F. Then let's try to make this brand new machine. So we're going to make a DFA. Me from the future here. I said right here that we're going to make a DFA for this language. I actually mean NFA. But the rest of the proof will be exactly the same. Carry on. For the half language. So I'm going to call it D over 2. That's the name of the DFA. I'm going to call it states Q over 2. Same alphabet because we're accepting strings over the same alphabet. It's just different strings, but it's the same alphabet. Transition function, delta over 2. Okay, this is starting to get a little silly, but f divided by 2. So I'm not literally dividing the set by a number, it's just the name of the set, so that we can distinguish between the original DFA and this one. So let's try to figure out what these pieces are. Well, the alphabet, that's pretty obvious. So what are the states going to be? So Q over 2, what is that going to be? Well, we need that initial state to be able to non-deterministically guess the possible choices that we can make. The initial state, the initial selection of a state from the original DFA that we had. So we're going to have that state be this one. So Q0 divided by 2. So that is the initial state. So let's write that down. So that is the initial non-deterministic state. The state that we're going to choose from there, what initial starting state from the original thing we're going to pick. So it's effectively this blue state out here. but in a different context because these states are going to represent different things. Okay, well, what else are we going to have? Well, we got to figure out, okay, what is the initial guess state? So I'm going to have, I'm going to union this with a set. So union with Q times Q times Q. And you may think, where did that come from? So this first Q, I got to keep track of all three possible things. The initial guess state, the one that we're currently in the first half of the computation, and the one in the second half. So this is the initial guessed state. And of course, because we initially guessed it, that is never going to change. So this guy is never going to change, ever. And we got to make sure of that. This one right here is the state that we are in the first half. And we want to have this one over here to be the state in the second half of the computation of the original DFA. And so what we're going to try to do is we're going to try to make it so that, well, the state in the first half, when we're done, should be exactly the same as this one, whatever the one that was picked here. And this one, it better end up at the exact same time in some final state in the original DFA. So let's write that down then. So the final states in this new thing, well, they're going to be, well, this set right here is just all ordered pairs. This is never going to be a final state because, one, we're going to epsilon transition anyway, so it doesn't matter. And here, this is where the actual work is doing anyway. So it's going to be all of the ordered pairs, ordered triples. So I'm going to call them P, Q, and R. So, well, the thing is that these two must be exactly the same. So P equals Q. In fact, I could even shorten that up. I can say P and R. So now I'm forcing them to be the same. And this state right here better have been an original final state in the D machine. So R was a final state in the original DFA. Okay, so that handles that. So then how do we actually do the transitions? Well, let's think about it. Well, this state is just going to have an epsilon transition to essentially any possibly guessed state. So let's think about how that would work. So let's change colors. So delta over 2, that's the name of the transition function. Well, let's see. So we have this Q0 over 2 state, which is going to be handled separately from everything else. So it's going to have a bunch of epsilon transitions, no other transitions. Well, let's think about what this is going to go to. So it's got to make a guess. So it's got to go to something in this set right here. Well, here, the second half, well, actually, let's start in the first half. So the first half must start at the initial start state from the original thing. So the middle coordinate here has to be Q0. So this has got to be Q0, followed, preceded, and succeeded by something. Well, it's got to be, whatever state's right here has got to be the same as this one. So the first one, which is the guess state, has to be the initial starting point of the second half of the string, of the computation. So whatever this state is, has to be exactly the same as the one over here. But the thing is, it could be any one of those states. It could be any of the original states at all. So what we're going to do is it's going to be a set. We're going to non-deterministically choose. So let's have that be Q as being an original state in the original DFA. And actually, I should make this an ordered triple because these states are triples, of course. Okay, well, that allows us to say the first half is going to start at the beginning. Whatever state we guessed as to be the midpoint, that's where the second half is going to start. And then what are we going to do about any other state? And if obviously we're not going to do anything else here because this is just going to make the guess, and then from there we're going to do the actual work. So here, let's think about what if we're in some arbitrary triple and we're going to read some symbol A. Well, what we're going to do here is, well, this and this first coordinate P, that should never change, right? So so this thing should never ever change because that was the initial guess. But on these two, we need to figure out, okay, well, this one needs to figure out where are we going to go on A. But this one on this second one, which is the second half, we don't care about what the second half has. So anything could be read from wherever this state R can go on any input whatsoever. Let's include all of those. So this set here is going to again be an ordered triple. The first coordinate is going to again be P because we are not going to change the initial guess. We're going to look up in the transition function the original one and say, okay, from Q on A, where are we going to go? But for the second one, we need to be able to go to any possible transition that R can do, because again, we don't care about the second half of the string. As long as it has some choice to make, then we're okay. We don't require that the two halves be exactly the same. So here, we're going to have delta of R, and this could be a different symbol, let's call it B, for any B in the alphabet. Okay, and I better close this off because it's an ordered triple. And you can actually see now that this must work. Why? Because this is the initial coordinate, and it clearly never ever changes once it's guessed here. So that's good. This is starting at the right place. This is starting at the right place. That's all good. This one is reading, is doing exactly what we should do, because this thing on A is exactly what the first half would have done on A, and we're only keeping track of what the first half is because that's what half of L is. It's only the first half. And the second one, we're reading one character, and so we don't care what it is as long as it has some character, which is good. And we have the final states are correct because whatever the initial state guess was, the place where we end up in the first half must be exactly the same as the initial guess because it should be in the middle half. And the one here has to be a final state, which means that the second half ended up in a final state. And so the two halves must be identical in length because we always read exactly one character on each occurrence. And so that shows, at least in an informal way, that it actually is correct. And you can do this via induction. I want to do an example though. And I have not cooked up this example. I'm just making it up as I go. I just want this to be a really simple example. So let's make a simple DFA for all strings that end in a 1 over 0 and 1. So let's have a simple thing like this. A really small thing because this is going to blow up pretty quick. So let's think about what the states are. So we're going to have, well, there are 2 states in each one of these. So there are going to be 8 states from here and then 1 more from here. So I'm going to have, let's do it in yellow. So I have Q0 divided by 2. That's going to be there. And so I'm going to have all triples from here. So I'm going to actually abbreviate them using the subscript. So if I refer to 000, that's going to be Q0 3 times. So I'm going to have 000, 001, 010. Oh, this is going to be horrible. 011, 100, 101, 110, and 111. Okay, so now let's do the final states because that's the next thing on the list. It's all of the ones which have identical first 2 coordinates, and the second one is a final state in the original thing. So the one that was final state originally was a 1. So anything that ends in any state name that ends in a 1 and has identical first two coordinates, I'm going to make final. So this guy is going to be final because it has a 1, ends in a 1, and has identical first two coordinates. Does not end in a 1, does not have identical first two, does not end in a 1, doesn't have the identical first two, does not end in a 1, has identical first two, so this one is a final 1, 2. Okay, so then now we're going to have an epsilon epsilon transition from this guy to every single state. And what I'm probably going to do is I'm going to have the epsilon transitions be a different color so that it's pretty obvious what I'm doing here. Okay, I think that's all of them. Okay, so then now let's see. So now what we're going to do, so we handled the green transitions, now let's do the blue ones. So we got to figure out where each one of these states goes on 0 and 1. Triple zeros. So the first coordinate is going to always be 0. Let's write that down. The second coordinate is going to be what the 0 state would have done on the corresponding character. So let's think about 0. So where does it go? So 0 is going to go to wherever this goes, it's going to be transition 0. The third coordinate is going to be whatever the 0 state, wherever the 0 state can go at all. So wherever the 0 state can go at all, that's where it's going to go. So here, effectively, we're going to have a self loop here on 0 and a 0 going to there also. Because the first coordinates are 0, so that's okay. We're looking only on input 0, so this second coordinate dictates which state to look at. So this one says wherever this guy goes on 0, which is itself, so the second coordinate must also be 0. And then now we look at the third coordinate and see where does that go. So the 0 state can go to itself or to the 1, but we're only considering input 0 because that's what the second coordinate is dictating. So here we have a 2 0 transitions. Okay, so then now let's focus on 1. So on 1, again, we're going to have starting coordinate 0. We're going to figure out where the second coordinate goes. Well, that goes to Q1. So it's going to be 0, 1 something. So then, well, where does the third coordinate go? So 0. Well, where does that go? That can go to 0 or 1. Same as before. So on input 1, that can go to here or to here. Cool. And actually, one thing that's kind of interesting is that we're going to have a little NFA over here on these 4 states, these 4, and then we're going to have another one over here because the starting coordinate never changes, which is kind of cool. In fact, they're going to be kind of mirror images of each other because the DFA to start with is kind of symmetric, but that's beside the point. All right, so let's think about this for 0, 1, 0. Actually, no, let's do this one. So on input 0, where does this thing go? So this thing, let's see. So the starting coordinate 0, so that never changes. This 0 says Q0 on input 0, where are we going to go? The second coordinate is always going to be 0. And then whatever the third coordinate is, whatever the 1 state would have done. So whatever the 1 state does, well, that goes to both states. So effectively on 0, we're going to have something that looks like this. So it's effectively that these 2 states are kind of similar to each other because the DFA is kind of symmetric at the beginning anyway. And then on input 1, well, it's effectively going to do what this state would have done. Okay. So it's effectively what, let's just be sure. So starting coordinate 0, this state on 1 is wherever the 0 state would have gone on 1, which is Q1. So it's going to be one of these 2. And wherever this state would have gone on anything. So this is going to go here because that's what the 1 state would have done. And 1 there. All right, so then what about these 2? So 0, 1, 0. How about I just do these 2 and I'm not going to do the other 4 because they're extremely similar. Just change the which ones it actually goes to by swapping the zeros and ones. So 0, 1, 0, where does that go on input, let's say 0? So the starting coordinate is going to be 0 again. This thing is wherever the 1 state would have gone on 0, which is the 0 state. And so the second coordinate is going to be 0 always. So wherever this thing goes on 0, it's going to be one of these two. And the 0 state, which is the third one, it can go to any one of the two states because that's what the original DFA did. So these 0 transitions just go back up. And then the 0, 1, 1, oh, actually, no, we didn't do the 1 transition. So the 1 transitions, so the 0 is not going to change. The 1 here is telling us where to go from state 1 on 1, which is itself. And so it's going to be one of these two states. And the ones in the 0 state can go to either of 0 or 1. So that's going to have 1 here and a 1 there. And it's pretty obvious what's going to happen next. But let's just be sure. So let's see where this state goes on 0. So starting coordinate 0, that doesn't change. The 1 thing here tells us from state 1, where do you go on 0? You go back to the starting state Q0. So the second coordinate is going to be 0. So this 0 transition is going to go back up. And the 1 state can go to either one of the two states on 0 again. So I know it looks horrible, but it's very, very symmetric. And if you minimize this thing, it's actually going to be quite small, which is good. And now, what about on the 1 transitions? It's pretty obvious what this is going to do. So I don't need to fill that in. Okay. So, and if you did the exact same thing over here, it'll be very, very similar, except you flipped the 0s and 1 transitions around on the corresponding things. Remember, the first coordinate, you can might as well forget it, because the transitions are going to only be among these over here. And they're never going to go to this other half over here. And because the DFA up here is so symmetric, you can flip the 1 and 0 transitions around and it'll be identical otherwise over there. Okay, so that was a quick proof, well, quote unquote quick, to show that if you have a language L and you divide by 2 by taking only the first halves of the strings, that is regular. And we were able to show that by having an example DFA. And we built a NFA. Actually, I should have said NFA up here. That was my mistake. We're building an NFA, and you can convert it back to a DFA, of course, because NFAs and DFAs are equivalent. Hopefully that was interesting. Leave comments down below about anything related to dividing by 2 in languages and NFAs and DFAs. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.